it's kind of dense. There's a lot, I have a lot to show you in StatCrunch and a lot to show you in the calculator as well. So buckle up. 6.1, confidence intervals for the mean when the standard deviation is known. And remember, this little sigma is the standard deviation, and that is the population standard deviation. Okay. Let's get a few vocabulary words. We've got a point estimate. That's going to be a single value that estimates a population parameter. The most unbiased point estimate of the population mean is the sample mean. Okay. That way, we can estimate the population parameter with the sample statistic. Okay. Let's see how this works. We've got a researcher. He's got a random sample of 40 student athletes, and he's recorded their number of hours spent on required athletic activities for 1 week. And we're going to find the point estimate for the population mean mu. So the population would be all the student athletes, right? This is only 40. So we're using the sample to estimate the mean number of hours spent on this required athletic activity. So all we're doing is finding the mean. And that's the sample mean, 19.9. That means the point estimate for all student athletes is going to be 19.9. Point estimate. So based on this sample, we're going to say that the mean number of hours of required athletic activities for all the student athletes is 19.9. That's going to be important as we kind of move forward a little bit. It may seem a little bit discombobulated here in the beginning, but just hang with it and we will get into some good stuff. So I told you we were doing confidence intervals. What are they? Well, they start with an interval estimate. What is that? It's going to be an interval or range of values used to estimate a population parameter. So we say, okay, I think my population parameter is in between this interval. That is what we call an interval estimate. Before finding a margin of error for an interval estimate, first determine how confident you need to be that your interval estimate contains a population mean mu. Now, here's a word that we've introduced, a margin of error. So we've got the margin of error. I'm in between these two values. So my margin of error is here to the mean and here on the higher end to the mean. So this little distance here is our margin of error. That right there. Okay. All right. Just in case you didn't kind of catch what that meant, we're going to do more on it as we progress. But first, we need to find a level of confidence. So this is going to be the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. We use critical values for this. Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. All right, what does this look like? If we have a confidence level of 90%, what we'll do is we'll find, and this is the rejection region is what we'll call it, the rejection region. And this critical value is going to define where we will reject and where we will fail to reject. Excuse me. I couldn't get the words out. But how do we find this critical value? Well, you go 1 minus the confidence level, which is 0.1. And then we're going to multiply that by half. So there's half on the left side and half on the right side. We just split it in half, okay? Then we find the area in that one tail. So this area here is 0.05. So we're going to look that up in the table. I don't have a table handy, but we would look up 0.05 inside the table. Remember last week we looked inside the table to find the z-score? Well, that's what we would do here in this case. But let's use technology. We love to do that. Let's start with the calculator. Let's clear all that out. Oops. And we said we had a confidence level of 0.9. Here we go. So here you would do second vars, inverse norm, and then you're entering in the mean, 0, the standard deviation of 1, because this is normalized, and then comma, we want to go center. So second catalog, this is how I get to center, and C for center, and you see center right there, and then close the parentheses. Oh, wow. Wait a minute, I didn't put something in here. I didn't put something in there. Okay, here we go again. Second vars, inverse norm, and I was supposed to put in the 0.9. That's why it gave me that strange answer. The area, then 0, the mean, then the standard deviation of 1, and then I will do second catalog and go to center. Boom. And that gives me my two critical values that separate what's probable from improbable. Okay, that is the calculator. Now, let's look at StatCrunch. All right, I'm already here. Normally when you open it up, it'll open up to standard. You will go to between, you will put your area. Oh, let me back up a little bit. You're going to go to stat, calculators, normal. Then you go to between. I'm going to put in my area of 0.9, and I get the same answer, negative 1.645. That's my Z critical on the left, and my Z critical on the right is 1.645 as well. Okay. Let's look at question 3 in the homework. And it says, find the critical value Z necessary to form a confidence interval at the level of confidence shown below. Okay, our C is 0.87. So just let's look at our calculator. And here again, you're going to go inverse norm. So second vars, inverse norm. My C is 0.87. It's normalized. So we've got a mean of 0 and standard deviation of 1. And I'm going to do second catalog and center. So that's second 0, which is the catalog menu. And then enter. This Z critical value that they're looking for here is the positive side. So it's 1.51. If the level of confidence is 90%, this means that we are 90% confident that the interval contains the population mean. So what's probable is this everything in blue and this kind of peachy looking color, that's the improbable. And the corresponding Z-scores are plus or minus 1.645. in this case. And we're going to need this as we progress. So sampling error, what's going to be, or it is, the difference between the point estimate and the actual population parameter value. The sampling error is the difference of X bar and mu, the population mean. The population mean is generally unknown. It is, and X bar, or the sample mean, varies from sample to sample. So let's look at question 5 and see how this is going to present itself. Okay, notice we have used the values on the number line to find the sampling error. Remember, the sampling error is X bar minus mu, the mean, the population mean. So let's pull this up. And what we would calculate is X bar minus mu, okay? And that would be the sample standard deviation, the sample mean, excuse me, minus the population mean. That's all you do. And so we put that in our calculator, 4.3 minus 4.58, and we get negative 0.28. Okay, easy enough. And that would be question 5, and question 6 is going to be the same. So we have something called the margin of error. And this is going to help us to build a confidence interval. It's sometimes called the maximum error of estimate or error tolerance. You might see that verbiage somewhere, but in general, nowhere in the homework you'll see that. So the greatest possible distance between the point estimate and the value of the parameter, it is by estimate, excuse me, it represents the greatest possible distance between the point estimate and the value of the parameter. It is estimating, denoted by E. All right. So here, remember when we found Z critical value? That's here. This is where we're going to need it. And so make sure you remember how to get it with the calculators. There's your Z critical value. And then we have the standard error of the mean, or the standard deviation divided by the square root of n. And this is provided that the sample is random and the population is normally distributed, or n, the number of data points in your sample, is greater than 30. So let's calculate this value. So it says use the data from example 1, and that was the student athletes, remember, to find the margin of error for the mean number of hours spent on required athletic activities per week by all the athletes. So assume the population standard deviation is 2.4 hours. Okay. Now we're going to apply that formula to find the margin of error. Remember, we talked about the margin of error kind of at the beginning. And the Z-score that corresponds to 95% confidence level is 1.96. How do we know that? Well, we could jump into StatCrunch and we could do 0.95 here. And that gives us a negative 1.96. Or you can do inverse norm on your calculator. And that will, on your TI-84. And that will get you the 1.96 Z-score, the critical value. All right. And so we take that critical value, 1.96, and we multiply it by 2.4 divided by the square root of 40. 40 is our n value. This gives us our margin of error, which is 0.7. So now what you do with that margin of error is you add it and subtract it from the mean. So I'll take my margin of error at 19.9. and I will subtract away 0.7. And for the other end, I will add 0.7. Right. This gives it to us in words, but I wanted to see how this plays out. Here we go. All right. And so there's my left endpoint, and then there's my right endpoint, X bar plus E, and then X bar minus E. That's how you find the confidence interval. So now what we can do is actually put this in the calculator or put it in StatCrunch to find the confidence interval. Let's put this problem in there, and let's start with StatCrunch. So stat, Z-stat, one sample, can't see it. Stat, Z-stats, one sample with summary. My sample mean was 19.9. My standard deviation they gave me was 2.4. The sample size was 40. I'm going to click on confidence interval for the mean mu. And we were at 0.95, right? Yeah, 9.95. I always in StatCrunch do show critical value just so I see it. You can calculate it by using the calculator in StatCrunch, but here is my lower limit, 19.2, and my upper limit as 20.6. So that's how you find it in StatCrunch. Now, in the calculator, we're going to go stat, tests, and Z interval. And I'm going to put in this information from this problem. So we have standard deviation was 2.4. The X bar was 19.9. N was 40. And the confidence level is 0.95. Notice that as I'm typing in the values, it's changing this lower and upper value. If you have a data set, like it's in list 1, you'll just click on data and it'll pull your data from list 1. And that's how you do a confidence interval in StatCrunch and the TI-84. Any questions on that? We will do another example as well, but I just wanted to stop and just make sure everybody's on the same page. What did we just calculate? We calculated the margin of error. By hand, we can do that. And we can also calculate it with 2 modes of technology. All right. All right. So with 95% confidence, we can say that the population mean number of hours spent on required athletic activities is between 19.2 and 20.6. That was the interval that I found. Let's look at question 14. Okay, now question 14. They're asking us for 2 separate confidence intervals. So I'm going to open this little window here and open in StatCrunch. Unfortunately, if you have the TI-84, you're going to have to enter in this data, and you'll enter it into like list 1 or something, or list 2, whatever list you want to use. And then you'll calculate based off of that. And again, you can click on data on the calculator and it'll take you to whatever list you want to go to. All right, so we have stat, Z-stats, 1 sample with summary. And let's see if I can make this a little bit bigger. Confidence level, they wanted 90%. And the sample mean, oh shoot, I did with summary, but I have my data here. Stat, summary stats, if you have data. Z-stat, 1 sample with data. 1 sample with data. All right, my data's in var 1. Yay. Confidence interval, 0.9. Show the critical value just because I want to see it. and compute. Critical value is 1.645. And our confidence level is from 31.31 to 41.93. One decimal place, 31.3 to 41.9. Okay. And so what does that mean for us? It means that I am 90% confident that the population of U.S. workers age 16 and over who did not work from home and asked how long it takes them to get home from work, from home to work, is going to be between 31.3 and 41.9. I think, even though I have a sample of 32, I think I can extrapolate this to all of the workers. Okay. Let's try it again. We've got a college admissions director wants to estimate the mean age of all the students currently enrolled. He wants the mean age of all the students, but guess what? He only has a sample of 20. So we can use N in this case. Let's construct a confidence interval of the population mean age. You know what? We've got all our information on screen. So I want you to pull up your technology, whichever one you're going to use, and I'll give you about, let's say, 2 minutes to use your technology, and we'll see who's going to be the first person to type in the confidence interval for the population mean age. Now, what are the things that you need? You need X bar, which is here. X bar. You need your standard deviation, which is 1.5. You need your N, which is 20, and your confidence interval. Usually we put 0.9. C equals 0.9. Or did you have to pull up StatCrunch or the calculator? And your screens on your calculator might look a little different than mine. Okay. So let's look at StatCrunch first, and then we will look at stat, Z stats, and we're using Z because the population standard deviation is known. When we know the population standard deviation, you're going to use Z. One sample, this time it's with summary. And we'll check you out, Michael, and see, what was this? 22.9, standard deviation was 1.5, sample size was 20. Confidence interval, it was 0.9. I like to show the critical value and compute. So what do we get? 22.3 and 23.45. That is correct. That's your lower limit, 22.3, and your upper limit is 23.45. Okay. In our handy dandy calculator, get rid of this. We want to go to the standard deviation, which we said was 1.5. The mean was 22.9. N was 20 in this case, and 0.9 was our confidence level. So there again, we have the 22.3 to 23.45. All right. So make sure that, when we're trying these, you try them on your calculator, because if you come up with any errors or anything, we can work those out while we're here, and make sure we understand what to do with these problems. Okay. So with 90% confidence, I can say that the mean age of all the students is between 22.3 and 23.5. Remember, I'm estimating all with my sample. All right. The mean, population mean, is a fixed number. It is either in the confidence interval or not. It is incorrect to say that there's a 90% probability that the mean is in the interval. But it is correct to say if there's a large number of samples collected and a confidence interval is created for each sample, approximately 90% of these intervals will contain the population mean. So let's look at a picture of what that looks like. So here's the population mean there. There's the population mean. And I've got my intervals. This is my confidence interval number 1. This is another confidence interval. That one actually has the population mean. Here's another confidence interval. So what I'm saying is when I'm building a confidence interval, that this population mean is going to be somewhere in that interval. That's what I'm saying. And in the long run, 9 of every 10 such intervals will contain the population mean. Where's the one that doesn't have it? This one doesn't have the population mean in it, right? Because it's not crossing that red line, the third one down. Okay. Last part of this section, we're going to work backwards from our formula. Let's look at the formula that we had before. Here, the margin of error for the mean mu. For the mean mu. So notice we just worked backwards to figure out what n is going to be. So given a confidence level and a margin of error, we can come up with the minimum sample size n needed to estimate the population mean. So if n is not a whole number, then round n up to the next whole number. If the standard deviation is unknown, you can estimate it using S, provided you have a preliminary sample with at least 30 members. S is the sample standard deviation. Remember, this sigma is the population standard deviation. So we've got our student athlete sample. Remember, that mean was 19.9, and we don't even need the mean. Why am I saying that? The sample mean is within 0.5 hours of the population mean, so that is our margin of error, 0.5. And Z critical is going to be the 1.96. And our population standard deviation was 2.4 for that sample. So I'm just going to plug all that in. N equals Z critical times the population standard deviation over the margin of error, and we're going to square all of that. So that means it's 1.96 times 2.4 all over 0.5 squared. Okay, so what is that number? Oh, cover the numbers up. We've got 1.96 times 2.4, divide that by 0.5, and then square that, and we get 88.51. Did anybody get that? 88.51. And we're going to round up to the nearest whole number, so that means 89 is what the number we're going to look for. So right now, the researcher only had 40 He's going to need, was it 40? So he's going to need some more, some more people. His N needs to be 89. He only has 40 right now. Okay. Any questions on finding the confidence interval when the standard deviation is known, or finding the sample size? The sample size, you're just plugging into a formula. 7.1, and this is an intro to hypothesis testing. Hypothesis testing is a big part of what we're going to do. The confidence interval hypothesis testing basically is going to take us through to the end of the class. So it's very important that you get these concepts now so that they're solid when we start to build on them. Okay. What is a hypothesis test anyway? It's a process that uses sample statistics to test a claim about the value of a population parameter. For example, you're going to consider a manufacturer that advertises its new hybrid car has a mean gas mileage of 50 miles per gallon. If you suspect that the mean mileage is not 50 miles per gallon, how could you show that the advertisement is false? So what is the statistical hypothesis? It's going to be a statement about a population parameter. We're going to have a pair of hypotheses. One is going to be the claim. What are they claiming is going to happen? And the other is going to be is complement. And you'll see what I'm saying in a moment when we actually formulate what these hypothesis statements are. When one of the hypothesis statements is false, the other one is true. We call these the null and alternative hypotheses. Okay. A null hypothesis is a statement of equality. So you'll know the null hypothesis by the fact that it has an equality symbol. So that has equal sign, equals, equals. The alternative hypothesis, on the other hand, is the complement of the null hypothesis. And so it's a statement that must be true if the null hypothesis is false. It contains a statement of strict inequality. So notice there's no equal sign here. There's a not equals there. And there's no equal sign on the less than symbol. Okay. The symbol H sub 0 is read as H sub 0 or H naught. I never say H naught. I just don't. I had a professor that did. Either way is fine. Whatever's floats your boat. H with an A as the subscript is called H sub A. And let's look at 7.1. Question 4. Question 4. All right. Use the given statement to represent a claim. Write its complement and state which is the null hypothesis and which is the alternative hypothesis. So if I have a less than equal sign, what sign will represent the complement of that claim? And you can type it in the chat. It's on your keyboard. What sign would be the opposite of less than equal to? Yes, it would be greater than. Notice it's completely turned a different direction and it does not have the equal sign. All right, so of your choices, A through I, which is the null hypothesis and which is the alternative hypothesis? Hint, the null hypothesis has an equal sign in it. On D, you have an equal sign. So that's not the opposite of less than equal to. We found it up here, right? So our null hypothesis is going to be the less than equal to. The alternative hypothesis is its complement, so that's the greater than symbol. So that's going to be answer choice E. And the reason why it's not D is because D just has an equal sign for alternative hypothesis. But we know in the alternative hypothesis, there's going to be no equal sign. Let's try that again. You have an equal sign. What is the opposite of an equal sign? An equal sign or not equal sign. By the way, if you ever need symbols, you could go to symbolsalad.com and they have all these symbols here, like the not equal to. I could actually type this and put it in the chat and you would have a not equal to symbol if you wanted one. So not equal. So here you go. Check the answer. Okay. So now what is the null and what is the alternative hypothesis? A through I. What do you think? Got one answer. Okay, we've got some agreements here. Okay, got an agreement. Awesome. Okay. All right, we said it was G. That would be correct. All right, number 6. Question 6. Try it again. You have a greater than symbol. What is its complement? What is its complement? Less than or equal to. Now, all this time they've been giving you, the first one has been the null hypothesis, but this time they gave you the alternative hypothesis first. So A through I, which one represents the null and alternative hypotheses? All right, we've got a G, and yeah, G would be correct. Remember, it stumped you a little bit. The null hypothesis always has the equal sign. Okay. All right. So what we do is we, to write the null and alternative hypothesis, we translate the claim made about the population parameter from a verbal statement to a mathematical statement. Then we write its complement. So here are the different versions that we saw. We actually saw a couple of these when we were looking at the homework. See, P is greater than 0.48. And then what was this one? This is the standard deviation. And this one was the mean. They're really just trying to show you what the hypothesis statements look like. This is if less than equal to is the null, then the alternative is greater than. If greater than equal to is the null, then the alternative is less than. If the null hypothesis is equal to, then the alternative is not equal to. Or just some other ways to state this. And now let's try some of these. We want to know what's the null and alternative hypothesis. Well, a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. So the operative word is. What mathematical symbol do we use for is? This is that. What mathematical symbol do we use? Yeah, we use an equal sign. Okay, so our null hypothesis is going to be the proportion equals 0.61. This is our claim because they're saying it is 61%. Now, knowing which one is the claim and which one is not is going to be very important to you. So just kind of pay attention to which one is the claim and which one is not, and the reasons why they are not the claim. All right. And then the complement of equal to is just not equal to. Remember, the claim can be either the alternative or the null hypothesis. It doesn't have to be one or the other. All right, a car dealership announces that the mean time for an oil change is less than 15 minutes. What's my inequality symbol here? Right, we've got this, less than 15 minutes. Is that going to be the null or alternative hypothesis? If I say less than 15 minutes, is that going to be the null or alternative? Yes, 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 yes. Very good. It's going to be the alternative. I'm excited because this is the very, very basis of what we need to know to tackle hypothesis testing. All right, so the claim is the alternative hypothesis this time. What about this one? A company advertises that the mean life of its furnaces is more than 18 years. What is my inequality? What do you think? The company advertises that the mean life of its furnaces is more than 18 years. You are right. This is the alternative hypothesis, but the inequality is what? And I see, okay, in agreement, 1 and 2. You're right. So it is going to be more than, so that is the greater than symbol. So our claim is the alternative hypothesis because that's what we're claiming. And the claim will be obvious to you when you read each of the problems. And toward the end of the night, we're going to work these from top to bottom, and we'll find the null and alternative hypothesis. We'll write the hypothesis statements. We'll find the critical value. We will then perform the hypothesis test, and you can see what that looks like. Now, here is what they're showing. They're showing us the 3 examples, basically. So remember, when we had the proportion was 0.61, we're saying that the null hypothesis is that it equals, and then the alternative is everything else. And then when we had, I forgot what this example was, but 15 was our h sub 0 was greater than or equal to 15 on that one. And on the last one, we had h sub 0, or the null hypothesis is less than or equal to 18. So notice this black kind of hovers over the 18 because it equals that. And the alternative hypothesis is on the other side. Let's look at question 7. We're looking at question 7. Okay. So in this question, it says match the alternative hypothesis shown below with its graph to the right. Then state the null and sketch its graph. State the null hypothesis and sketch its graph. Yeah, this is really just number line stuff. If you remember the number line from even like Math 062 or, beginning algebra. So we're going to go A. And state the null hypothesis. What is going to be our null hypothesis if the alternative is greater than? Oh, shoot. I've run into the break. We'll finish with this question and we'll take a break. Okay, I got a less than or equal to. Great. And then sketch a graph of the null hypothesis. Which one is the null hypothesis? Right, we're going to go with B. Check the answer. This work. All right. They've given us an alternative hypothesis. Which one is it? A, B, or C? Which graph represents our alternative hypothesis? I've got one brave soul. What about the rest of us? Do we agree? Okay, one agreement. Looks like the majority is going with B, and that would be correct. No pun intended. B, because the variance, which is sigma squared, is not equal to 7. There's that. What is the null hypothesis in this case? What is the null hypothesis? Yep. A couple of, all right. You're right. It is the equal sign. Because they're opposites. Oh, and now we need to sketch its graph. What does this graph look like? One, two, 3 A's, 4 A's. Let's go with A, because it's equal to. That is correct. Okay. We'll come back to that. All right. When you perform a hypothesis test, one of two decisions can be made. You can reject the null hypothesis, or you can fail to reject the null hypothesis. And that's what we'll talk about here next. Well, we're going to talk about errors first. A type 1 error happens if the null hypothesis is rejected and it's actually true. The null hypothesis is rejected, but it's actually true. A type 2 error occurs if the null hypothesis is not rejected when it is false. Here's what that looks like. Type 1 and 2 error, just as in a graphic. Type 1 error is false positive. Rejecting a true null. Type 2 error, failing to reject a false null, false negative. Okay, you kind of see how that looks. He's telling the man he's pregnant, and not quite. And then this woman who's clearly pregnant, she's saying she's not pregnant. That's just how each of those works. All right, let's run some statistical tests. After stating the null and alternative hypotheses and specifying the level of significance, a random sample is taken from the population and sample statistics are calculated. The statistic that is compared with the parameter and the null hypothesis is called the test statistic. And all of this is going to make sense when we put some numbers and values to it. With the assumption that the null hypothesis is true, the test statistic is then converted to a standardized test statistic. It's going to be ZT, or they got chi-squared. That's what that is. This test statistic is used for making a decision about the null hypothesis. Okay, we're going to cover each of these. Today, we're going to get to 7.2, and we're going to be calculating hypothesis tests for when the population standard deviation is known. And we're going to be using the z-test. All right, p-values. What are p-values? Very integral to our process. It's going to be the probability, if the null hypothesis is true, of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. And again, we're going to see what this looks like. That might not mean anything to you right now, but probability value, or p-value, is going to be something that we'll cover extensively here. There's going to be 3 types of hypothesis tests. And the type of test depends on the region of the sampling distribution that favors a rejection of H sub 0, or it's going to follow the alternative hypothesis. So we've gotten pretty good about identifying the alternative hypothesis. In this case, the alternative is here. It's a less than. So this is a left tail test. You can tell that because here's my rejection region. And my inequality is pointing to the left. The inequality is pointing to the left, so it's a left tail test. Now, notice on when my alternative hypothesis is greater than, my inequality is pointing to the right. This is a right tail test. The alternative hypothesis is pointing to the right. So that's going to be a right tail test. And then when the alternative hypothesis is a not equal to, that is a two tail test. Let's go back to our examples. We said a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Is this a two-tailed, left-tailed, or right-tailed test? And if we recall, H sub 0 was P is equal to 0.61, and H sub A was P is not equal to 0.61. So left tail, right tail, or two-tail test, based off of the information we just learned. Right, it's a two-tail. We're not pointing in either direction, the alternative hypothesis. This is a two-tail test. Okay. Half the p-values area is in the left, and half the p-values area is in the right. What about a car dealership announces that the mean time for an oil change is less than 15 minutes? We recall sub 0, the mean greater than or equal to 15, and the alternative less than 15 minutes. Left tail, right tail, or two-tail test. Okay, got one vote. Left tail, right tail, or two-tail test. Remember, if you have an inequality, you're looking at, well, if you have a greater than or less than, you're looking at where the inequality is pointing, essentially. Left tail, right tail, or two-tail? Okay, we got some agreements here. Left. It is a left-tailed test. The p-value area, or the probability value area, is in the left tail. Okay. Last one. A company advertises that the mean life of its furnaces is more than 18 years. Left tail, right tail, or two-tail? All right, a couple of rights. Right-tailed. You are right. There's a right-tail test. P-value area is on the right. Okay. So very important rule, and we'll repeat this a million trillion times, and you want to have this written down somewhere. If the p-value is less than or equal to the significance level, or alpha, we also call this the significance level, then we reject the null hypothesis. If the p-value is greater than the significance level, and we will set the significance level, then you fail to reject the null hypothesis. All right, here is one of my favorite graphics, and I'm going to show you another way to write this to make it easier to put in your notes. This is the verbiage. Let's go back. When the claim is the null hypothesis and you reject H sub 0, or you reject the null hypothesis, then we say there is enough evidence to reject the claim. If the claim is the null hypothesis and we fail to reject it, we say there is not enough evidence to reject the claim. Then when we're talking about the alternative hypothesis, if that's the claim and we reject the null hypothesis, we're going to say there is enough evidence to support the claim. And then if we fail to reject the null hypothesis, we're going to say there is not enough evidence to support the claim. Here's a graphic that I like to use with my students because it makes it just easier to imagine the wording. And you can take a screenshot or you can write it down real quick, but it's essentially giving you the same information as you're getting in this table, but I've got pluses and X's and the verbiage on the side. So plus is enough evidence, R to reject, plus is enough evidence, S to support the claim. And then the X is not enough evidence, R to reject the claim. And then X is not enough evidence, and S to support the claim. So have this written down somewhere or take a screenshot with your phone so you can refer back to it later on today, because we're going to need this actual decision rule. And everything builds on the other. So I'm just giving you a few minutes to kind of get this little graphic. It's something good to have around. Okay. Okay. We're here. Hypothesis testing for the mean. Let's look and see about this testing. It's a little bit different with the calculator. Okay, so that rule again, if the p-value is less than or equal to alpha, then reject the null hypothesis. If the p-value is greater than or equal to alpha, then fail to reject the null hypothesis. This is something you want to have written down. If you haven't taken a screenshot, do so now. Or just take a picture with your phone, because we're about to compare some of these alpha significance levels with the p-value. Okay, so I'm just going to rewrite it on the screen. Okay. So they gave us a significance level of alpha equals 0.05, and they gave us a p-value of 0.0237. Do we reject or fail to reject the null hypothesis? H sub 0. What do you think? Do we reject the null hypothesis or do we fail to reject the null hypothesis? All right, I see 2 people venturing out. You are correct. It is going to be reject. 0.0237 is less than 0.05, so I will reject the null hypothesis. Now, alpha equals 0.01. Oh, well, I already revealed it. In this case, because alpha is 0.01, it is less than the p-value, or the p-value is greater than alpha, so you will fail to reject the null hypothesis in that case. Okay. After determining the hypothesis test, standardized test statistic, and test statistics corresponding area, do one of the following to find the p-value. For the left tail test, the p-value is the area in the left tail. For a right tail test, the p-value is the area in the right tail. And for a two-tail test, the p-value is going to be equal to 2 times the area in the tail of the standardized test statistic. And we'll see what that looks like in a second. So find the p-value for a left tail hypothesis test with a test statistic z equals -2.23. Decide whether to reject the null hypothesis when the level of significance is alpha equals 0.01. So this is going to be the area in the left tail, right? And we're comparing it to an alpha level of 0.01. Well, what we need to know is what corresponds to z equals -2.23. So this is -2.23. But we need to know what the area that corresponds to this is. And we found that last week. So let's go back to StatCrunch. Stat, calculator's normal. We got our less than, and then our z value is -2.23. And so 0.012, let's say 9, is the area. So the area in here is 0.0129. Then we're going to compare that to this alpha level. So P is equal to 0.0129. Alpha is equal to 0.01. Are we going to reject or fail to reject the null hypothesis? Which one is bigger? Oh, one person says P. P is bigger, so here. So I will reject or fail to reject the null hypothesis. Reject or fail to reject. And pull out your handy dandy screenshot. Right, in this case, we will fail to reject. Because the p-value is greater than the significance level. Okay. All right, we're going to find the p-value for a two-tail hypothesis test with a test statistic z equals 2.14. Now, in technology for this one, you're going to have to work backwards from what they give you. So it's a two-tail test. You're on the between calculator. Z equals 2.14. So what you're going to have to do is subtract this number 0.9676 from 1, because what you want is these outside areas, this one and that one. So you will subtract 0.9676 from 1 to get that. Let's look and see how that looks like. And you will get 0.0162. But what do we do with that? It's 2 times the area in the tail of the standardized test statistic. So it's 0.0324. Do we reject or fail to reject the null hypothesis in this case? And what they tell us, the significance level is alpha equals 0.05. Reject or fail to reject the null hypothesis? Alpha equals 0.05. And this is your p-value. Do we reject or fail to reject? Let's write the rules again. If p-value So which one's bigger? 0.05? Let's put them together. 0.0324 and 0.05. Which one of those is bigger? 0.05. So that means my inequality will open to the right. Right. So we will reject the null hypothesis in this case. Okay, okay. Moving right along. It's looking good so far. All right. So the z-test for mean mu is a statistical test for a population mean. The test statistic is the sample mean x. The standardized test statistic is z. So it's like we're finding a z-score again. Remember from last week or last lesson we had? When these conditions are met, sample is random, at least one of the following is true, the population is normally distributed, or n is greater than or equal to 30. This is our formula. This is another formula you're going to need to know, but also we're going to use technology, so don't fear. You can always check your calculations with technology. Okay. Let's do an example. Okay. Oh, okay. I'll give you a few seconds to read through this. I won't read it to you. We're going to start from the top. What is the null and alternative hypothesis and which one is the claim. They kind of give it to us here, right? Oops. Is less than 13 seconds. So less than 13 seconds. That means the alternative is our claim. So that means the null hypothesis is going to be the opposite of that, which is greater than or equal to 13. Now we find our test statistic, standardized test statistic. And remember that calculation is Z equals X bar minus mu over standard deviation of the population divided by the square root of N. So that gives us 12.9. Mu is the 13 divided by standard deviation of 0.19 divided by square root of 32. So calculations. What do you get when you do 12.9 minus 13 divided by 0.19 divided by the square root of 32? I'll give you a second to calculate that. And you're just calculating what the standardized Z statistic is. That's the 12.9 minus 13 divided by 0.19 divided by the square root of 32. Yep, Avery, that is what I have arrived at as well, negative 2.97. And so this is the Z-score that we're going to look up in the table. Without even checking the answers yet. And what was the test? Less than negative 2 point. I'll just put it all in there. So we get 0.00145404. Are we going to reject or fail to reject the null hypothesis? P-value was, we'll say 0.0014. So we're comparing 0.0014 to 0.01. Are we going to reject or fail to reject? Which one is bigger? P is 0.0014. Alpha is 0.01. So the p-value is actually smaller. Oh, yeah, yeah. 2 zeros in there. Right, so we will reject the null hypothesis. All right, so get your handy dandy little graphic here, and let's see what that means. The claim is the alternative hypothesis. So we're looking on the right column, and we are rejecting the null hypothesis. So our wording is, there is enough evidence to support the claim that its mean pit stop time is less than 13 seconds. And then we can do a couple of examples into the break. StatCrunch. All right. I want to go back to this screen. This one, this tells us all our answers. Stat, Z stats, one sample with summary. Sample mean was 12.9. The standard deviation was 0.19. The sample size, 32. And here we are, a hypothesis test. Notice before we were doing the confidence interval, now we're looking at the hypothesis test. But in StatCrunch, it just has an equal sign for the null hypothesis. You have to change the alternative. So you'll change the alternative, and in this box, you will put your population mean, what you're comparing it to. Show the critical value. Oh, alpha is 0.01. The p-value, they rounded, is less than the critical, is less than the alpha level. So we can see with StatCrunch that we get the same result. So you can do either method. You can calculate the Z statistic and go through the process that we just went through. You can go to StatCrunch and do it that way. And let's look at, let me see, where did I put the instructions? Okay. Let's go to the TI. And the TI calculator. I'm just gonna, because our information is there. You're gonna go to Stat, Tests, and Z test. Then you're going to enter in all of your information. So the population mean was 13. Standard deviation was 0.19. The sample was 12.9. Sample mean was 12.9. Our N was 32. And notice down here, right above like the parentheses, my test, it's reading a two-tailed test. I need to select a left tail test. So right here, it was two tail. This is left tail, and that's the right tail test. So there's left tail. Okay. We're going to do a couple of these. And there is enough evidence at the 1% level of significance to support the claim that the mean pit stop time is less than 13 seconds. Then we'll just go back and do a couple of examples, just going from the start to the finish. Rejection regions is going to be the range of values for which the null hypothesis is not probable. And we're going to use the Z critical value and the Z statistic. If a standardized test statistic falls in this region, the null hypothesis is rejected. A critical value, and we've already looked these up, separates the rejection region from the non-rejection region. Okay. Finding critical values in a normal distribution. First, you specify the level of significance, alpha. Decide whether the test is left, right, or two-tailed. Find the critical values, and that goes back to our rules that we talked about. Left tail, you're going to find the z-score that corresponds to an area of alpha. Right tail, 1 minus alpha. Two-tailed, half is half alpha and 1 minus half of alpha. Okay, here is the drawing. This is the sketch. If you have a left tail test, your rejection region is over here on the left. You have a right tail test, your rejection region is on the right. If you have a two-tail test, your rejection region is these two tails in the blue. So I think we've already done this, but it says find the critical value and rejection region for a left tail test with alpha equals 0.01. Well, if alpha equals 0.01 and this is a left tail test, then we're talking about, we can go straight to the calculators. Standard less than 0.01 is negative 2.33. That's our critical value. Find the critical value and rejection region for a two-tail test with alpha equals 0.05. So we can use the formula here. Half times alpha is 0.025 in each tail. The area to the left of 0.025 and the left of negative critical value is 0.025, and the area to the left of the second critical value on the second side is 0.975. Now, again, we'll go to the calculator. Oh, why does it turn off on me like that? So on this screen, if you're in the screen, just hit done. And what you can do is inverse norm. So second vars, inverse norm, 0.95, comma, 0 for the center, the mean, 1 for the standard deviation, and then second catalog center. And enter. Okay. So your critical values are negative 1.96 and 1.9595. Now, let's go back. This says find the critical value with a left-tailed test. You can also do left-tailed in your TI. So inverse norm, what was this, 0.01? 0.01, comma, 0, comma, 1, comma, second catalog, and now I'm looking for left tail. And then I get the same negative 2.33. Why is this important? Because we need that value so we can compare it to the Z statistic. What this is doing is telling us, okay, at negative 1.96 and 1.96, those are my cutoff points. If there's anything outside of those two, then this is in my rejection region. Okay. Okay. So in our graphic, if you have a left tail test, the rejection region is on the left. The fail to reject is the kind of peachy looking color here. Right tail test, rejections on the right, fail to reject in the middle, and in the middle you fail to reject. On the outsides you reject on a two-tailed test. Okay. Let's try it. We have employees at a construction company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $95,600. Random sample of 20 of the company's mechanical engineers has a mean salary of $93,300. Assume the population standard deviation is 9,500 and the population is normally distributed at alpha equals 0.05. Test the employee's claim. All right, top to bottom. We're going to use the rejection region method this time. I got a little more room here. What is the claim? What is the claim? The mean salary is less than. So is that the null or alternative hypothesis? It is the alternative. So the mean is less than 95,600. So alternatively, the complement of that is greater than or equal to 95,600. So we got our claim. Great. All right. Now we need our Z statistic. And that's equal to X bar, 93,300 minus 95,600 divided by 9,500 divided by the square root of 20. What do we get when we put that in the calculator? We agree. I concur. Thank you, Avery. Negative 1.08. Now, okay, so here's our mean, 0. We got negative 1.08. We need to figure out what this alpha of 0.05, it's a less than. So what is the critical value for 0.05? Well, let's go here. And this time I'm looking for the critical value of 0.05. It's a less than test. It's negative 0.1645. So that's my cutoff. Negative 1.645. That is my Z critical value. Where is negative 1.08? Where is negative 1.08 on this number line? Imagine this is a number line. Where would it fall? To the left or to the right of my Z critical value? Yeah, it's going to be on the right. So I'm like right here, right? Negative 1.08. So that means, am I going to reject or fail to reject? Where does that test statistic fall? Is it in the rejection region or the fail to reject? Hint, I shaded the rejection region. Yep. We're going to fail to reject. Fail to reject. So this is the fail to reject region. That's where it fell. Okay. So let's go back to our handy dandy graphic and see how do we word our solution. The claim was the alternative, remember that. So you're in the second column, alternative hypothesis. Second column. And we are failing to reject here. So the verbiage goes, right, is not enough evidence to support the claim. There is not enough evidence to support the claim. And that's how we do the rejection regions. And there's the verbiage. There is not enough evidence at the 5% level of significance to support the employee's claim that the mean salary is less than $95,600. So we've got two ways of doing these problems. You can use the rejection region, or you can use the p-value. But of course, you'll have questions on your assignment that have both. We got another one. Let's go from top to bottom. All right. A researcher claims that the mean annual cost of raising a child between the ages of 1 and 3 in the U.S. is $13,350. In a random sample of families in the U.S., the mean annual cost of raising a child between the ages of 1 and 3 is $13,186. Sample consists of 1,000 children. Assumed population standard deviation is 2750. At alpha equals 0.10. Is there enough evidence to reject the claim? All right. So what is the null and alternative hypothesis? Right? That's the number that goes with it. Yep. Is so. I want to write before we look at the answer. Okay. Yeah. So if the null is equal to, then the alternative is not equal to. Which one is the claim? The null. You are correct. Because it says the researcher claims the mean annual cost is 13,350. So we're just pulling out this information from the problem. Okay, then we calculate our Z statistic. And that is 13,186 X bar minus 13,350. The mean mu all over the standard deviation divided by the square root of 1,000. What is that value? $13,186 minus 13,350 divided by I got a different number. Let me show you what I came up with. Let's make sure my math is right. 13,186 minus 13,250. Yeah, it's about negative 1.89. Oh, okay. Yeah, that'll do it to you. So, is there enough evidence to reject the claim? So we are here. So what are our two? What's our critical value? And how do you find it? You can use technology to find the critical values. Remember, half P, half alpha, excuse me. So you would be looking at 0.05 on this end. And then it's the same thing on the other end. So let's look at StatCrunch in the calculator. So StatCrunch at 0.05 on the left side, I have negative 1.645. So that's what I'm looking at here. It's 0.05 in the middle. Let me erase that. So this is negative 1.645. And so on the other side, this is 1.645. In the calculator, second vars, inverse norm. I forgot what I put in here. I think it's 0.901. Second catalog, center. And there you have it. So notice I didn't put in 0.1, I put in 0.9. So it's slightly different from StatCrunch to TI-84. I had a brain fart there. So when you're looking at StatCrunch, there's two separate ways that you can do it in StatCrunch. There's the standard, and then what you're going to look at is that I have half alpha over here. So my alpha in this place, on this side is 0.05. I just divide 0.10 by 2, and then I put 0.05 in the area field, and then hit enter. Oh, let's go through all the steps. Sorry. Stat calculators, normal, and that left side is 0.05. And so the left side, you define that, and you've got the right side too. So negative 1.645. I believe in the between calculator, you'll put 0.9 and you get the same thing. And we can use the between calculator because we have, it's a two-tailed test. So where does negative 1.89 fall? You're welcome. Where does negative 1.89 fall? Further to the left. Is it in the rejection region or the fail to reject? Yeah, it's right here. It's in here. I'll draw an arrow over there. Is this negative 1.89? It is in my rejection region, so I'm going to reject the claim. Now, what are the words that we use to reject the claim? What are the words that we use? Let's go back to our graphic. The claim was a null hypothesis. And we are rejecting the null hypothesis. Yeah. Is enough evidence to reject the claim? Is enough evidence to reject the claim? That is correct. So that's the way we do it in critical value. But again, there's two ways to do this. So if you wanted to use the p-value method, z-stat, one sample with summary, put in your sample mean, which was 13,186, and the standard deviation, which is 2750. The sample size was 1,000. Hypothesis test not equal to, and this should be 13,350. I want to show the critical value, and the significance level is 0.10. And compute. So notice we got our critical Z, it says 1.645. It should be negative 1.645 and 1.645. The Z statistic, we got that, negative 1.89. The p-value is 0.0593, which is less than 0.10. So that means we reject the null hypothesis. So you can use the p-value method, or you can use a rejection region. Oh, okay. Okay. So is there anything else I need to show you in the calculator again? Because we can go back to this one and walk through the steps. Where'd it go? So stat, test, z-test, and the population mean is 13,350. Standard deviation, 2750, 2750, 2750. And the sample sample mean is 13,186. N was 1,000, 2, 3. And we get the same p-value and the same z statistic using the TI-84.